Hello, everybody. Welcome back to some of you. Welcome for the first time for some of you. A couple of you have been in my webinars before. A couple of you are new. Hi, Jordan. Hi, Ananya. Today we're going to be talking about clocks, gears, gear ratios. What is it all? How does it all work? And how can you use it? Hi, Ian. Welcome. Hello, Aubrey. So the first thing is, what is a clock? Simple question, but it's worth looking at. So let's look at what is a clock? It's used to tell time. You want to know what time it is, you look at the clock and it will tell you, but there's more to it. There's more to how does it do that? Well, it's got three little hands and they each represent different things. One's an hour, one's a minute, one is the seconds. And they move at different speeds. And that's what's really interesting, is how do they move at different speeds and all be coming from the same thing? Well, that has a lot to do with gears, and that's what we're going to get into. So let's talk about gears. What are gears? This is a gear. I realized that one of the gears I brought for this was green, so it took on the background. So I'll show you a different one. It's a little bit easier to see. But this is a gear. It's something usually round, not always, and it has these little spikes on the edge. They're called teeth. And what these teeth allow you to do is you can connect up multiple gears, and then when you move them together, the teeth will cause the other gear to spin. The benefit of this is that you can send motion from one place to the next place, and you can actually change the speed that they're turning. For example, if you have this little pink gear and this orange gear, you see I have these two arrows on them? Well, watch how many times it takes the pink one to go around before the orange one goes all the way around. The pink one starts going and it's going all the way around, and the orange one is moving pretty slowly. So the pink one has gone around once now, and the orange one is not quite a fourth of the way. And so we keep going. It's gone twice. We keep going. We've gone 3 times now, unless I missed one. And we've gone 4 times and they meet back up. So what that's telling us is that this pink gear is moving 4 times faster than the orange gear. Hello, Moi Mao. So depending on the size of the gear, you can change that. So that's a 4-to-1 change in speed from the orange one to the pink one. If we take a blue one, the blue one is a little bit smaller. So this one actually only changes by a factor of 3. So that gives you a lot of capability. We're going to talk about something called ratios in this webinar, so it's important to understand what those are. So I'm going to go into some other slides. Let's go over here. I see Evan in the comments said you're 9, but this November 27th you'll be 10, and your passions are mechanics, technology, and science. Those are awesome passions, Evan. I have very similar passions. Okay, so that's clock, that's a gear. Now let's talk about ratios. If you have these 10 people in a room and there are 7 boys and 7 girls and 3 boys, you split them up. So now you have the 7 girls on one side and 3 boys on the other side. You can compare the amount that there are by taking those numbers and using this symbol that's right in the middle there between the 7 and the 3. It's called a colon. And this whole thing, the 7 to 3, is called a ratio. And it's just really a comparison of amounts. So you could say the ratio of girls to boys is 7 to 3. Or if you had a class with 10 adults and 5 children, you could say the ratio of adults to children is 10 to 5. Okay. We have a couple comments in here that are interesting. Evan says there are 2 ways in English to say gear. That's pretty interesting. American is gear and British is cogwheel. Huh, I like that. Katie says, I don't know if this is normal, but my passion is quantum physics. Quantum physics are incredible. There's a lot to learn in quantum physics and a lot that gets really, really interesting and kind of shakes your mind a little bit. Gerard says, is the basic of the gears that the smaller the gear, the shorter it takes to spin? Yes. So the smaller the gear, the faster it's going to spin, and the larger the gear, the slower it's going to spin. That's exactly right, Gerard. AG is saying, what about simplifying ratios? That is an excellent question. We're going to get right into that. Gerard says the ratio can be 21 to 18 if you multiply by 3, right? Yes, you can totally multiply ratios. So if you had a 7 to 6 ratio and you multiplied by 3, you would get 21 to 18. It goes the other way for simplifying. So let's say you had 10 adults and 5 children. Well, AG, you're exactly right. You could simplify that ratio by dividing each side by 5. So if you take the 10 adults and divide them by 5, you have 2. And if you take the 5 children, you divide by 5, you have 1. So for every 2 adults in the room, there's 1 child. And that's the simplest version of that ratio, is 2 to 1 is the ratio of adults to children. Thank you. So in gears, that's pretty important to understand. Jordan says, if the biggest gear moves the slowest, are there bigger gears for the slower moving hands? Yes, that is exactly right. But the problem we run into is that you would have to change the size of the gears really a lot in order to make it the right size. So let's talk about that. Thank you, Jordan. How many minutes are there in an hour? 60, right? So if you wanted to have, okay, well, let me back up a little bit. Thank you, Ian. Yes, you're right. So on a clock, the hour hand goes around and it goes down 1 number for every hour that it goes, right? So by the time it's gone through half the day, it's gone to 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, it hits the bottom, 7, 8, 9, it's over here, 10, 11, 12, 12 o'clock, it's gone for 12 hours, and then it's gone 1 full circle. Well, in 12 hours, the minute hand has gone around way more than 1 time, right? Because it's going, for every hour, it's going to 5 minutes, 10 minutes, 15, okay, half an hour, it's at the bottom, 45 minutes, and then an hour goes by and the minute hand has gone around 1 full time. So in 12 hours that it takes the hour hand to go around once, the minute hand, which takes 1 hour to go around, has gone around 12 full times. So if you wanted to make that gear ratio, it would be pretty challenging to get a gear that's 12 times bigger than the one next to it. You could do it, but it might be hard to fit it into a clock. So there's a solution for that. The solution is that we can stack gears up. It's a little bit tough to see, but I'll see if I can show you here. So what this is this set of gears has 12 teeth on each one, and this set of gears has 12 teeth on the top gear and 24 teeth or 36 teeth on the bottom gear. Yeah, this one's 36. So for every time that this one goes around 1 time, it will do 12 of the 36 teeth here. So this hand has to go around 3 times to make the red gear go around once. So that's part of the way. We're at a 3-to-1 ratio, but we still need to get to 12-to-1. So what we do is we add in another gear. And the way we keep that motion is because this little cylinder in the middle that these gears are connected by is called a shaft. And if you turn 2 gears that are on a shaft, they're going to turn at the same speed. So even though this smaller gear on top is a 12-tooth gear, it's going as fast as the 36-tooth gear below it. So when you turn this blue gear, this red 12-tooth gear is going 3 times slower. So we're already a little bit of the way there. Now, if we add this gear on top, this large blue gear has 48 teeth compared to the 12. So if you take 48 and 12 and you reduce them down, you end up with a 4-to-1 ratio. So this blue gear, the big one, is going to go 4 times slower than this red one goes. And this red one is already going 3 times slower than this little blue one is going. So if you take 3 turns of this little blue gear, then you've done the red one once. So this one, this big blue one, is a quarter of the way there because it needs 4 turns of the red gear. So we do it 3 more times. We go 4, 5, 6. Good. Now this one has done, the red one has gone twice. So this big blue one has gone half of it because it still needs to get up to 4 to do 1 full turn. So we keep going. We go 7, 8, 9. Okay, now this red one has gone 3 times. And this big blue one is getting there, but it's not quite there yet. It still needs to get up to 4 turns of the red one. So we keep going. 10, 11, 12. Okay, so now this red one has gone around 4 times, which means that this big blue one has gone around once. So it takes 12 turns of this little blue gear to make 1 turn of this big blue gear, which means we have a 12-to-1 ratio. So that's how you can end up with a larger ratio without having to necessarily have a gear that's 12 times bigger, because this big blue gear is 4 times bigger than the 12-tooth gear. So imagine if you had to make it 3 times that size, and then imagine if you had to make a bigger ratio, like 60. You'd have to make a huge gear compared to the 12-tooth one. Okay, Gerard says, it takes 60 seconds for the seconds gear to revolve fully, an hour for the minutes gear to revolve fully, and 12 hours for the hour gear to revolve fully. Am I getting that right or not? Yes, that's exactly right. So it's 1 full minute for the second hand to go around once, 1 full hour for the minute hand to go around once, and 12 full hours for the hour hand to go around once. That's exactly right. Okay, so that handles the ratio from the hours that they're going to go around once. Then we want the minute hand to go around 12 times. So that handles that part. Katie says you could just make the gears really small, right? Yes, you absolutely could. And that is actually in a lot of clocks. If you open them up, the gears are super small, way smaller than I expected. When I first opened a clock, I was like, wow, these are tiny. They are super small. However, to make it all even smaller, you can stack them up like this. For example, in a clock, this might be fine because these are bigger than you would need them. But if you shrink them down, that would fit pretty easily. And even if you did have to make it to a much bigger gear, you could still put it in a clock and it'd probably be fine. But what about a watch? Watch has to be a whole lot smaller, which means that you need to conserve as much space as you can. So that's where it becomes really helpful to stack them like this. AG says, if the small gear turns faster than the other small gear, how does the energy from spinning the first gear turn into more energy? That's a fantastic question. What happens is that it changes how much effort it takes to spin the gear. So this little gear here, this one is really easy to spin, and it spins really fast with very little force. And then as it starts going slower and slower, it's going slower and slower, but with more power. So this one, as it's going slowly, has a lot more power than this small gear going quickly, but with very little power. Does that answer your question, AG? Gerard says, the gear background behind you is in what machine? I actually have no idea if this background is from a real machine or if it's just some gears that were thrown together. I looked on Google Images for gears and I thought that this image was cool. Good, AG, gotta answer that. Okay, so let's get into changing now from minutes to seconds, because that one becomes even more complicated than going from the hour hand to the minute hand. So like we said earlier, it takes 1 hour for the minute hand to go around once. What about for the second hand to go around once? Well, we said that that's going to take 1 minute. As the seconds go by, it's going 5, 10, 15 seconds, 30 seconds, 45 seconds. 1 minute's gone by, the second hand has gone around 1 full time. And that happens how many times in an hour? 60 times in an hour. So it takes 60 turns of the second hand for the minute hand to go around once. Evan says if the small gear spins faster, will the other gears would move faster? Yes, they would. So the faster you spin the smaller gear, the faster it's going to do all the other ones. But as you can see, even if I try and spin that really fast, this bigger gear is not going super fast yet. As we expand this, see if you can kind of see that there. This black gear, I can spin really slowly and it sends a lot of really fast motion to the other side, even though I'm barely spinning the slowest gear over here. Okay, so we want to we're up to right here. This is where the speed of the minute hand is. We're taking this as the speed of the hour hand if this is the minute hand. Well, we need a 60-to-1 ratio. So that's going to take a little bit more work. Gerard says, is the gear going fast because of its size or because of its velocity? Well, its velocity has to do with its speed. So that's impacted by its size because of whether it's bigger or faster and the size of the gear it's connected to. That's going to change how fast it's going. So those are pretty closely related. Velocity is how fast something goes in one direction, right? Yes, velocity is a speed and a direction. So the velocity of the gear will be impacted by how fast it's going, or sorry, how big it is. Okay, so Katie says, wouldn't the last gear spin all the others the fastest? Yes, it would. So you can see from spinning, let's say I spin this big one in the middle, it spins these ones over here pretty fast, but not as fast as they could go. If I spin the next one over, they start to spin a little bit faster. I know it's a little bit shaky on the screen. I'm not sure how much you can tell. If you spin this black one, they go the fastest they can with the least motion over here. So that's how that works. Okay, so we want to get this 60-to-1 ratio. Well, we got the 12-to-1 ratio by taking a 3-to-1 ratio and combining it with a 4-to-1 ratio. So we can tell that by multiplying ratios together, we can create bigger ratios. So for example, the 3-to-1 ratio and the 4-to-1 ratio, you just take whatever numbers on the left side. So in this case, a 3 and a 4, and you multiply them together. 3 times 4 is 12. So you have 12 on that side. And then you take the other side, the 3-to-1, so we take 1, and 4-to-1, so we take 1. And 1 times 1 is 1. So we end up with a 12 from 3 times 4, and 1 from 1 times 1. And you have a 12-to-1 ratio. Oh, good, Ananya, I'm glad you fixed that. Thank you. Okay, so if we want a 60-to-1 ratio, we're going to have to multiply by another number. Well, we already know how to get a 12-to-1 ratio. So we could try multiplying by a 5-to-1 ratio and turn that 12-to-1 ratio into a 60-to-1 ratio by taking 12 times 5 is going to give us 60, and 1 times 1 is going to be 1. So by taking our 3-to-1 ratio over here and then adding a 4-to-1 ratio right next to that, and then we're going to add even another one, and combine that with a 5-to-1 ratio. And the way we're doing that is this, I'm going to put these down so I can hold this up. This is a 12-tooth gear, and this is a 60-tooth gear. So 60 divided by 12 will tell us that for every 5 times the small gear goes around, the big one will go around once. So if this goes around 5 times, this will go around once. We have a 5-to-1 ratio. So if we combine all of these together, this will give us the ratio that we need to turn seconds to minutes. If we look at that, you can see that it does actually change the speed pretty significantly by moving this big gear pretty slowly. We can get this 12-tooth gear over on the end going pretty fast. When I was first working with this, I ended up getting it so fast that this little 12-tooth gear would start spinning out of control and it would fly off of here. So you can definitely generate a lot of power with gears. Evan, yes, 3 times 1 is the 12 ratio and 12 times 5 is 60. Yes, exactly. So if we look at this whole thing together, I know it's a little bit harder to see on the screen than if it's in person. But let's look at what's going on all the way through here. First off, we have our 12-tooth gear connected to our 36-tooth gear. So that's going to be 36 divided by 12 is a 3-to-1 ratio. So we have 3. And then connects this 12-tooth gear to a 48-tooth gear. So that's going to be 48 to 12, or 48 divided by 12 is 4-to-1. So we have a 3-to-1 ratio and a 4-to-1 ratio. And then here we have a 12-tooth gear connected to a 60-tooth gear. So that's going to be 60 divided by 12 is 5. So a 5-to-1 ratio. So we have 3-to-1, 4-to-1, 5-to-1. And then down under here, you can't quite see it from above, there is another 12-tooth gear connected to this 36-tooth gear. So that gives us another 36 to 12 is 36 divided by 12 is 3-to-1. So we have a 3-to-1 ratio, a 4-to-1 ratio, a 5-to-1 ratio, another 3-to-1 ratio. And then over here, there's a 12-tooth gear on the bottom of this, and that connects to this 48-tooth gear. So 48 divided by 12 is 4. 4-to-1 is another 4-to-1 ratio. So let's look at multiplying them all together. So we get 3 times 4 is 12. And then we take our 5-to-1 and we do 12 times 5 is 60. And then we have our second 3-to-1 over here. And 60 times 3 is 180. And then we have our second 4-to-1. So 180 times 4, we end up with 720. So for every 720 turns of the small gear, this black gear turns once. Okay, we have a couple questions I'll answer. Gerard says, what kinds of boards are the gears on top of and how do they join with each other? Good question. These are 3D printed boards. You were in the last webinar I did earlier this morning, so I talked about this a little bit, but this is part of the clock that I printed, and so all of these pieces are 3D printed to work with each other. And these boards fit together very simply. They slide together. They have little holes in the bottom, and then little sticks sticking out on the sides, and then they just match together like that, like a little bit like a puzzle. So then they combine together. That's how that works. VS, welcome. How much does a 3D printer usually cost? 3D printer is usually a couple $100 to a couple $1,000, or sometimes more, up to a couple $100,000 or more if you're looking at a big industrial one. That was actually the 3D printing webinar was this morning. We're talking about clocks and gears, which you're welcome to be in here for. Okay, so does anybody have any questions about how this whole setup works? If you do, just go ahead and put them in this Q&A section. And if not, we'll get into how to actually incorporate this into a clock. Evan says, make the small one fly off for us. I don't know that this will do it because I tried to fix it so it wouldn't do that much, but we can see. So we'll go, it's jumping a little bit. We'll see. I don't totally want it to fly off. Ian's asking, how does the black gear make it faster? Okay, so what's happening is you have this bigger gear of the black one next to, it's connected to a smaller gear. You can see that there in this blue one. And because this black gear has more teeth or more of the spikes on the edge, then it connects to this one with less teeth, and it spins it around more times for every time this goes around, because it only takes 12 teeth going by to spin this one full time. But this one passes 48 teeth by it in a single turn. So it does enough for 4 turns of this blue gear. So that means that the blue gear is going to go 4 times faster than the black gear. And then that kind of transition carries out through the whole set of gears, and it keeps building on itself. So for every spin of this blue gear, it will be even more spins over here, which will then be more here and more here and more here, until it's eventually 720 spins over here for every 1 spin here. Gerard is asking, it goes from 3-to-1, 4-to-1, 5-to-1, 3-to-1, and 12 to 4, right? Close. It's 12 to 3 or 4 to 1 on this last one. This is 3 to 1, 4 to 1, 5 to 1, and then another 3 to 1, and then this one is a 4 to 1. Leah says, is that a green screen behind you because the green gear has the same background? Sorry for the off-topic question. No, yes, you're exactly right. I thought that was really cool when we first turned this on, is that the green gear took the background. Yes, I thought that was really interesting too. Okay, so yeah, this I brought this green gear just as a demonstration of how they change, how many times it takes the pink one to go around for the green one to get all the way around. Okay, so putting this into a clock, there's even a little bit more math that goes into it. Because you then have to figure out, well, this is the mechanism, but how do we get that to actually turn the hands of a clock? And that part gets really interesting because you can't have, we have the right speeds going on here. This one's going really fast. So this would be the seconds hand, which goes the fastest. And then this one is going 60 times slower than this really fast one over here. So that would be the right speed for the minute hand. And this black one is going 12 times slower than the minute hand, or 720 times slower than the second hand. So that would be the right speed for the hour hand. But if you had a clock that had the hour hand in one place, then the minute hand, then the second hand, that would be really confusing to read. So somehow we have to combine them all to get all the hands sticking out from one place. The way that works is by connecting them to even more gears. So we looked at how if you have two gears of different sizes and you move them with each other, it's going to change their speed, right? Well, that's fine, but what if you put two gears of the same size? Like what if, let's see if I can pull up two of the same size. What if we have these two gears? These are the same size. Well, if they move together, their speed is actually not going to change at all. So in order to change the place that this motion is coming from, we could take a gear of one size and connect it to a bunch of other gears of the same size, or connect it to a bigger gear and a smaller gear, and then eventually end up at a gear of the same size, and the speed won't change at all. So that lets us figure out, okay, well, now we can move the motion. So we can take it from having the second hand speed over here, and we can put that closer to a middle point. But how does that then end up working if you want to put something else in the same spot? Well, I forgot to bring it down, but there's a really interesting way to do that. And what it takes is putting the shafts of the gears inside of each other. So you have one gear, it looks almost a little bit like this. You see how this has 3 gears on it? Well, you would have something like this, and each of these gears, except instead of being 3 of different sizes, it would be all the same size, and they would be connected to gears that are spinning at the right speed. And instead of having this shaft all connected, it would be like one shaft and then a smaller one inside of it so that it can rotate around itself. And then another one inside of that so that they can all rotate around that. And then that ends up coming up through the clock. I know it's a little bit confusing without something to really show it, but go ahead and ask if you have a question on that. Gerard says, also the black gear backfires my hypothesis about the bigger the gear, the slower the gear moves. In a way it does, but you're actually right about the slower it is, the bigger it is, but we can change that a little bit by adding the layers on there. So you could have, for example, these 2 gears, and if it's just one flat gear not connected to another gear, the bigger one is always going to be the slower one. There's no way that you're going to have them moving like this, and the bigger one is going to be the faster one. However, if you add a second gear on top of here, so you have something like these 2 gears moving together, you can then have these gears connected, making this one go slower, And then this gear, which is the same size as the one over here, because this one's connected to the fast one and this one's connected to the slow one, this small gear will move slower than this gear of the same size. So your hypothesis is right. It just needs a little bit of qualification of saying that they have to be connected only to each other. Evan says the smaller gear, it goes faster. Yes, that's correct. So yeah, that's how that works. And then if you were to stack a lot of gears on top of each other and connect it to lots of gears, like maybe something like the background behind me, you could get some really interesting speeds going on. And then that's how you end up with things like in a car. You have lots of gears in the car and they move at different speeds. And that has to do with being able to change the speed of the gears by connecting them. That's another example of somewhere where you would need to have lots of gears in a small space. Gerard says, oh dear, we're almost out of time. We are almost out of time. We're running pretty short. And yeah, so that's how the actual math behind it goes. And then if you connect them up and you get them coming from one place, that's pretty much all that it takes to put a clock together. And once you understand the math behind it and the ratios and how to work with those, it becomes a lot simpler to think about, okay, well, how do you have all these things going at different speeds coming from the same spot? So if you ever end up with some gears around you to play with, try messing with them. Try putting together some different ratios and see what you can create. It can also be pretty satisfying sometimes to set up the gears and turn them. It's pretty fun. Okay, so we are almost out of time. We have about 10 minutes left. So if you have any questions, things that I covered that you didn't quite understand, or things that I didn't cover that you wanted me to cover, go ahead and ask them now and I'll see if I can hit them. And yeah, so that is that. The other thing that you can do with this kind of gear ratio is you can, besides putting in a clock, you can create kind of anything that you want to go at a different speed. So if you're trying to get something going way faster than you could get a motor to turn, you can set it up with a number of different gears to get the ratio up really high. Evan says, that was a long time ago when the first car was invented because the cars only have pipes and cables to the motor. Yeah, that's true. It has changed. And there are still some gears, like in the turning mechanism, that involves some gears. And it doesn't involve as much of the layering like this. But you're right, it has evolved. Sarah says, could you give us the basic way that motors work and how they connect to gears? Good question. So motors, depending on the kind of motor you get, it will work differently on the way that it turns. And I don't have quite enough data on all the different kinds of motors to get into that. But if you have a motor turning, it is essentially just a rotating motion. So you could have even a motor that doesn't have a gear connected to it, and it would just be a shaft and you could connect a gear to it. For example, I had a motor when I was trying to put the clock together. I had no way to power it besides turning it manually, which doesn't work very well to create a working clock. So I got a motor that had a turning shaft, and I got a gear like this and just put it right on the motor. And then when the motor turned, the gear would turn. And then when the gear turned, I could connect it up to other gears. And then that power from the motor would power these gears. And even though it wasn't very fast, it was turning pretty slowly. It was turning, I think, slower than I needed the hour hand to move. But it was enough power to then make it really fast through the rest of the clock down to the seconds. Evan says, are you teacher Dylan's sister? I'm actually teacher Dylan's daughter. And I do have a brother, but I don't think he's done any webinars, but he's also interested in very similar stuff of video game design and 3D printing and math. He also is into that. But yeah, so it's definitely helped me being Dylan's daughter, because he's very smart and helps get me interested in lots of things like this. Moima said I missed something 5 minutes ago. No problem. What did you miss? Gerard has a joke for us. He says, why did Father Time throw the clock? See time fly. That's a good one. Sarah says she did Dylan's 3D modeling class. That's awesome. Were you guys doing Blender in that one? Yeah, he's done some of 3D modeling classes. He also does game development classes, and those are pretty fun. Good for kind of any skill level. Sarah, in Dylan's 3D modeling class, if you guys were working in Blender, that's the program that all of these were designed in. So we were working in Blender to build all of these and then printed them from there. Via says he sells games on Steam. That's awesome. You create them yourself? That's very cool. Yeah, so if you're, the other thing you can do is if any of you guys have done the 3D modeling class and you're interested in doing more in Blender, you can set up physics engines in Blender to then run the gears. So when I was starting to create this clock, I set up a physics simulation and gave it a motor and put all the gears in the right place to see if it would actually work with the right ratios before I tried printing anything. So that was a lot of fun to see all the different kinds of things that you could do with that. Evan says, what day will teacher Dylan make the class of Pico 8? I think he's doing them on Wednesday, Thursday, and Friday next week, but I'm not positive about that. Moy and Maya said you don't know. No problem. Well, if you realize what you have a question on, you are totally welcome to ask. Yeah. So that's about all that I have. You're welcome to stay in here. We can keep chatting for the next 7 minutes, or if you have other things you want to talk about. Gerard says, when is our next class with you? I will be doing some webinars next week. I'll probably be doing one on Blender next week, and we could get into a little bit of how I created the gears and how to work with that. I'll also be doing one on computer basics with spreadsheets, and then I might be running one of the book clubs too. Evan says, joke, what does a clock say to the other? I don't know, what does a clock say to the other? Sarah says, me and my family are going swimming now. Bye. Thank you for coming, Sarah. Have a lot of fun swimming. Gerard is asking, will you do more physics? I could do more physics. Is there a specific part of physics that you want to learn more about? Time's running. What does the clock say to the other? Time's running. Okay, VS, have fun. Yeah, if any of you guys have specific other physics things that you're interested in, I'd be happy to learn about it. Bye, Evan. Gerard, you want to learn more about robotics? Okay, that could be fun. Like Lego robotics, like that kind, or you want to do something with a lot more intense coding or the physical part of it. That could be really fun. That also ties in well with 3D printing, actually. If you want to 3D print some pieces, that gets really exciting. Evan says, did you know a person named Sylvia in Delphi? Yes, I've met some people named Sylvia. I've met a couple people named Sylvia. Evan, have you been to Delphi before? Sylvia Pimentel, I don't recognize the name. Alan says you want to learn about coding. Yeah, coding is super interesting. I know a little bit, but not nearly as much as my dad. So I think he's been doing most of those. And those would be great to tune in on. Gerard says, I want to learn more about Lego connections. Okay, that would be cool. Oh, Evan, that's cool. No, I don't think I've met her. But I'm sure some people here have if she's been up here. Gerard says, your whole family works at Delphian. Almost. Both my parents do and I do, but my brother is a student. I was a student recently and then I graduated and I was going to leave and then I realized that I really, really love it here and that one of the best things that I felt like I could do for the world would be to help people have a similar education to the one that I got because it was really beautiful for me. So I realized that this was probably the best place for me to be. So now I'm here and I'll be doing college classes as I'm working here and continuing to move on up and be engaged that way. But yeah, it's pretty great here. Gerard says, Delphian rocks. I totally agree. I think you would love it too. Ananya says, you want to learn more about gears. I think gears are awesome. I would be happy to do another seminar on gears if you have specific parts of it you want to get into, or if you want to try building something. I did one seminar with a group of students here on gears, and we got into a little bit of what we've gotten into today and expanded it a lot more. And then I had them design some gear ratios of their own and then set them up, and we printed them and they could see the gear ratios that they had created. And that was pretty cool. Evan, you have Pico 8 and Delphi rocks. I totally agree, Delphi rocks, and Pico 8 is also awesome. I'm glad that you like doing that. I think that's a really great intro programming and game dev platform. Okay, well, we have just a couple more minutes. So I want to show you guys this. Let's see if I can get in here. Oh, we went through that. Oh, this is from Heron Books, which is where the Delphi curriculum comes from, but they make lots of curriculum that any educators can use and students can buy and parents can buy. They have some math courses that will help a lot with things like gear ratios, not directly gear ratios, but they'll talk about ratios and how to work with them, which is super helpful for trying to work with gears and design. So that is definitely, if you're interested in math and you're interested in mechanics and these guys that are really into that, these would be great to take a look at. Gerard says, I wish we could do it for the next hour or two. Yes, I definitely love talking about gears and printing and design, and I would love to do it for a while. I'm glad you can't wait to tell your family. That would be awesome. And then you have this math book. That's awesome. How do you like it? You're gonna make a Sonic X remake, Evan. Oh, wow. That will be really cool. Moy and Mao, you love video games, do I? I don't play a lot of video games, but I have definitely played some because my dad's really into it, my brother's really into it. And I'm really interested in what goes on behind the scenes of creating the game and the art and the music and how much that plays into it. There's a lot of art there. Bye, Gerard. Enjoy your lunch. Alan says pulleys and levers. That would be awesome. I would be really interested in getting into that and talking about some other simple machines. Ananya says, it's very good for a math book. Good, I'm glad to hear it. I think that these courses are really awesome and helpful. Ian said, like what? I think I missed the earlier comment that I was referring to. Gerard says, I forgot what's your name. My name is Quinn. Okay, we are really running out of our time, so we've got to end off so they can start up the next ones. So goodbye, everybody. I've had a great time chatting with you and learning about this. I'm totally happy to do more. If you send in some comments on which classes you would like, then we can get them set up, and I would love to do some more with you. Moy Mouse says, you love math. I love math too. I'm glad that you do. Okay, goodbye, everybody. Feel free to send in any comments of what you would like to do next and in the future, and we'll be happy to deliver it.